Okay, so this carries on straight from the last video. In the last video, I kind of went through the process by which I came up with our hypothesis invariant, and so I am now satisfied with the logic that if I can prove through induction that this is true, that I will guarantee the post condition. So if you didn't quite follow that, just watch the previous video again. But basically, if I can prove that this is true here, 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 and here, then it will be true by induction, and then my entire thing works out, and we're all happy. So, with writing these proofs, it's like super weird. This y is greater than or equal to 0 doesn't really matter for this. But you kind of start with what you're going to want to end up with. So, what I want is at this point, I want z is equal to a times x. And I want to prove that that's true on account of the fact that z and a are both going to be 0, right? So even just looking at it, you can kind of tell that it's going to be true, but we want to kind of like show that it will definitely be true. So kind of starting up here, knowing that we want to get to here, they always do this thing where you don't just, so after they write a equals 0, they don't then introduce a new condition where they say a equals 0 before a equals 0. They write 0 equals 0, and then through substitution, sub in a for 0. It's just kind of like making it really annoyingly verbose. But so I would start, if we've got kind of our statements here, let's say that a equals 0 is here, and then z equals 0 is here. What I want, man, I cannot even, okay. What I want is here, for me to be able to say z is equal to a times x. And actually I'm going to leave a little bit of room for that, because I'll need to write something. But z is equal to a times x. So, to prove that, what I'm going to want to make sure that I have directly above it is a way to substitute 0 for z. So above it, I'm going to want 0 equals a times x. Right, because if I have 0 equals a times x, up here, then when I show that z equals 0, I can now translate this really easily into that, kind of in this like fundamental building blocks of logic. So if 0 equals that and z equals 0, then z equals that. So that's kind of like the statement that will immediately come before that, because that's kind of how we're using this substitution here. So one up from there, we're going to want to do the exact same thing, but with a. So if we have 0 is equal to 0 times x, and a equals 0, then if I can move this whole thing down for a second, let's see if I can. Totally legit. So now I'd be able to go 0 is equal to a times x. For the exact same reason, kind of like this step to this step is exactly the same as that step to that step. We've got 0 that I'm substituting out for a, because they both equal 0, and down here I'm substituting out this 0 for z, because that equals 0. And you don't have to substitute all the zeros. Just because I've substituted one a in here doesn't mean I have to substitute the other one. But I kind of like, I always end up writing these in this weird kind of like backwards iterative way. So I start at where I want to end up, which was here. And then I kind of go to the previous statement and say, okay, what steps do I need to show that? Okay, well, what steps would I need to be able to show that? And then kind of all the way up the top here, you just kind of end up with this, like, 0 is equal to 0 times x, and 0 is equal to 0. So if you have that 0 is equal to 0 there, and then a is equal to 0, we can kind of like swap that out for a is equal to 0. And like I'd then go and neaten that up a bit. I think the actual solution is a little bit different this is like a bracket example, but that's kind of the way that I go about writing these things. So let's just say that I went back and neatened this up, give it some better structure. So we now have z is equal to a times x at this point here, which is our kind of like our first hypothesis proof point, because that is this one here, just underneath z is equal to 0. So now, if you kind of remember back to the previous video, the 3 points I want to prove it at, I want h0, hk, and hk plus 1. So, next we want to just keep going. So then we get while a does not equal y. And so naturally, our assertion here is that this hasn't changed. Z is still equal to a times x, and a does not equal y. The thing is, though, the whole a not equaling y thing is not actually really relevant. All we want to prove is that this statement maintains its integrity through to the end. So we actually don't really care about that at all. And so they keep writing in the proofs this like, it tripped me out when I first saw it, but it was just P and Q implies Q or P. They usually do P, I think. P and Q implies P. And that's just really obvious. It's basically just saying, if I have proved at this point the sky is blue, and water is wet. Sorry, it's getting really many. So if I've proved the sky is blue and water is wet, then it's also fair to say just that the sky is blue, right? Because if both are true, then this one must obviously be true. That's all that P and Q implies P mean. If you kind of think of the truth table, it's like this is true, true, false, false, true, false, true, false. Then you get, obviously, the result true here and false for the rest. There are no situations where this is true, where Q isn't true, or P isn't true for that matter. So also P and Q implies Q as well. That's just two sides of the same coin. So all of that means is just that if you've already proven two things, you're allowed to just also claim that you've proven one of them. So all of that's just not super useful to think about specifically, but it just means that you can drop sections of your AND condition, because if I've proven that both of these are true, and I just don't care about that, then this is still true. Nothing has changed that. So, then we come down to our next statement, which is, what have we got? Z is equal to Z plus X. So, here, we just use a simple substitution into the previous one, and so we now get Z plus X is equal to A times X, and that's just through some really obvious substitution. And then our next statement, A is equal to A plus 1. So again, if we just substitute this in, Z plus X is equal to A plus 1 times X. And that's just by, again, direct substitution for the a for a plus 1. So now if we just actually expand this, expand the brackets there, just with some real basic math, we get z plus x is equal to ax plus x, or a times x plus x. And then if we minus x from both sides, which we can do because math, we get z is equal to a times x. And lo and behold, that's the end of our statement. So if we jump across to our other color here, we proved it for h0. We proved it for h of k. We just dropped this other term because it just sits there, not changing. It's just not relevant. And then we proved it that after all the changes the loop makes, it's the same. So these 3 points that it appears at is just why the invariant is now true, because if you remember this whole time, that's been our hypothesis. I just said that if that was an invariant, that it makes our postcondition true. That's kind of like my I hope this is true, because that makes my stuff work. But now I've proven that it's true, because it's true for h0, hk plus 1. Now that's proof by mathematical induction, which means that it's no longer my hypothesis invariant, it's just my invariant. And if you remember back to the previous video, that means we can take it outside, so we end up with z is equal to a times x and a is equal to y. And then you substitute in the a for the y, z is equal to y times x. And that's kind of the end of your partial correctness proof. I guess I may as well write up that last part just because we've already come so far. So what we end up with is, so now that that's p and not b, right, just due to our loop rule, we know that not b is the opposite of the loop condition. The loop condition is that a does not equal y, so we know that a is equal to y. And p, which we've just proven, p is our invariant, z is equal to a times x. Therefore, z by basic substitution is equal to y times x. I've just given up on the curly brackets, and that was our initially required postcondition, and that is a partial correctness for this algorithm. So the biggest step for me was just finding the hypothesis, then going through the motions of proving that hypothesis is true is really just some like super basic simple math, and trying to show all of these kind of dumb steps to make it irrefutably true, I guess. But hopefully that clears some stuff up.